Good morning. Good morning. What I'm going to do in this brief session is talk about the ideal gas law. Now, I know there are probably lots of presentations involving the ideal gas law, but this is my view of it, and you'll get a different perspective from me than from anybody else. Every man and his dog has a different story. So, the ideal gas law essentially describes the behavior of a, let's say, fixed mass of gas. You can vary the mass, but let's say a fixed mass of gas when the configuration of it changes. What does that mean? Well, what kind of things can we use to describe a gas? In retrospect, I can tell you that they are pressure, volume, and temperature, and amount, whatever amount means. The word amount doesn't work very well in physics. In physics, we just have mass or volume in terms of amount. But amount is good here because it's mixed up with another concept, which we'll talk about later, and that is the mole. Basically, we're beginning to look at the ideal gas law in terms of the 17th and 18th century vision of a gas. And that is as a compressible fluid. A compressible fluid, like you can take a bicycle pump and you can compress this and none of it escapes. In the 19th century, that's the 17th and 18th century viewpoint, sorry. In the 19th century, the ideal gas was viewed as a collection of particles, which later turned out to be molecules. And some of the characters involved in this will be Robert Boyle, 1627 to 1691. He was Anglo-Irish and born in Waterford. He did many other things. He was a great innovator in chemistry. Jacques Charles, French, 1746 to 1823. Hamilton and Gay-Lussac, they have the same kind of law, and it's kind of mixed up. It's not sure who exactly initiated it, but it's nowadays known as Gay-Lussac's law. We have another law due to Amedeo Avogadro, who was Italian. These two guys were also French. This idea, Avogadro's idea, will involve amount of gas, volume of gas, later the idea of the mole, mu. We can name it N if you want to. And the idea of a mole is a very subtle idea. A lot of people who studied chemistry, when they don't fully grasp the idea of the mole, they waltz through chemistry and don't ever quite get the gist of an awful lot of the things that they do. The idea of a mole is subtle, simple, but once again, takes a little bit of effort to get your mind fully around it. So, C1 is going to be a constant. Something is going to be constant due to Boyle. C2, that's going to be a constant. C3, another constant. C1, C2, and C3. So let's look at Boyles Law. Boyles Law. So we can take a fixed mass of gas, and for convenience we'll put it into a container, which is basically going to be a cylinder. With a piston, which we can compress if we want to. Let's put a weight on this. Let's say it's 1 kilogram. No gas can get in and out of this container. The mass of it is fixed. The mass of gas does not change. In the 19th century point of view, that would mean that the number of particles in there doesn't change. But we're not dealing with that yet. We haven't got to that stage yet. This is before the idea that mass, that this was composed of molecules or particles. People are not viewing it that way. It's a compressible fluid, kind of fluid. It's a gas, but it's compressible, and we're not quite sure what's its nature. What kind of things would we measure with regard to this? In here we could measure the volume of the gas. We'll denote that with the symbol V, and volume is going to have units of length cubed. We're not using litres, we could. Cubic meters is what we're using. Now, we have a weight on the gas, pushing down on the gas, but that means that the gas is returning the effort to support that weight. We'll talk about the force that the gas exerts on the kilogram, but not quite the force. We'll talk about the force per unit area. Force is measured in newtons. Area is measured in units of length squared. Meters squared in this case. And these units are given the name pascals. Actually, force per unit area could be like this: 10 newtons per square meter, 100 newtons per square meter. We'll call that pressure. Okay? Pressure is a force distributed over an area. What else could we measure in here? P is going to be the symbol for pressure, by the way, not pascals, it's just pressure. Well, we could stick a Bunsen burner down here. And we could heat it up. Or we could immerse the whole thing in a bath of ice. We could put ice all around it and cool it down. We could heat it up, cool it down. We could change its temperature. Now, I'm not going to talk about the units of temperature just yet, because we will look at new units of temperature when we study Charles's law. We'll just denote this as the symbol T. So, the state variables for this fixed mass of gas are pressure, volume, and temperature. And we're going to look at some function of these variables that will describe the evolution of an ideal gas. Now, this is an ideal gas, so therefore, in reality, it can only be approximated by a real gas. Good enough for us, though, for now. I'm O'Reilly, by the way. I'm not using any high-tech stuff. I don't even do PowerPoints. I like a live presentation. It could be for an elementary topic such as the ideal gas law, or it could be an introduction to quantum field theory. I don't care. To me, the live presentation, even if it involves some small mistakes which you can correct, is better. You get eye contact, you get the dramatics. It's like a live performance on stage as opposed to lip syncing. It's different between Madonna and Elton John, let's say. So for an ideal gas, we have pressure. volume and temperature, describing the state of the evolution of this gas when it's in the box or cylinder. Let's start off with our gas at pressure P1, whatever that might be. Let's say 100 by 10 to the power 3 pascals, who knows. V1, cubic meter, and temperature T1, 300. 300 what? I'll tell you later. Now let's do Boyles Law. Boyles Law basically says this: if I double the pressure on the gas, I'll have its volume. Yeah? If I quadruple the pressure on the gas, I'll get 1/4 of the volume, or roughly, or proportional to that. Boyles Law says that P times V is a constant. And that was the constant C1 that you have in your notes from earlier on. I can write that C equals P1 over T. It's an inverse law, inversely proportional to the pressure. The volume of a gas is inversely proportional to the pressure on it. If we didn't mention something, do you see temperature involved here? This is only true at constant temperature. And a graph of this would look like this. Depending on the mass of gas, of course. Okay? That's our first law, Boyle's Law. We'll go to our second law. Charles's law. Charles's law states the following: if we experimentally examine how the volume of a fixed mass of gas varies as we cool it down, in other words, temperature is on the x-axis, horizontal axis, and volume is on the vertical axis. Now in centigrade, let's begin 0 degrees C, 100 degrees, whatever. So at a certain high temperature, we could measure the volume of a gas and get a reading and plot it. Cool the gas down further, and we can get a set of points. Charles' law says that all these points lie in a straight line for one mass of gas. For a different mass of gas, let's say twice the mass, you get another set of points. And for another mass of gas, another set of points. And remember, this gas is all the time in our cylinder. We're in that cylinder, and we vary this time the temperature and the result is that the volume decreases. So that the volume decreases with decreasing temperature, and not only that, all these graphs can be extrapolated. Even if we don't have points back here, we can say, oh, if we cool the gas down even further, there is one point back here where they all converge. What happens down here? Let's see what the volume is. Could I extrapolate down to here? I don't think so, because we cannot have a negative volume. We have to have a positive volume, so only positive volumes exist in the real world, in the ideal gas world. Now, in practice, of course, what happens if we start cooling down nitrogen? Eventually, nitrogen goes through a phase change, becomes a liquid, and it becomes incompressible. That's not the ideal situation. We're pretending that this gas just is totally ideal and it does not go through a phase change. Carbon dioxide, you start cooling it down, eventually it becomes a solid, right? That's not an ideal gas. The ideal gas behaves like this. Now, this magic number back here on our scale in centigrade is negative 273 degrees. So let's do something now. We're going to rescale this entire graph so that, see, centigrade begins arbitrarily at the freezing point of water or melting ice. That's an arbitrary situation. We should have, if we wanted to invent a scale, begin at the starting point for all temperatures, the beginning of all temperatures. Below this, no temperature exists. So we'll move our guy back here. So where the old centigrade was is now at positive 273 degrees C. Sorry, we're not calling it C anymore. We're keeping the width between the little dashes the same. They're still the size of a degree, but we'll give this new name K for Kelvin, after Lord Kelvin. We did some work on temperature, on heat. So this is the Kelvin scale, volume versus temperature, but plotted in Kelvin, and when that happens, we get a straight line graph through the origin. We can now state Charles's law. This is a straight line. What's the equation of a straight line through the origin? Well, y equals some constant times x, if that was an x-axis and this was a y. But it's not. This is a v and this is a t. So we relabel the constant m to be c1, we'll change the x to t, and we make volume the v. So that when t is 0 on the Kelvin scale, v equals 0. This point is called absolute zero. When I say point, I mean a position on the volume temperature grid. Let's get rid of this now because we've got a statement. We're going to label that C2 because we had we had Boyles Law, we labelled the constant C1. Now we have V over T because I can rewrite this by dividing both sides by T. Look. They cancel. V over T equals C2. Charles's law. We have one more law to go through. The law of Gay-Lussac. Now I forgot to mention one thing. When we look at Charles's law, there is no mention of P. He is kept constant for Charles's law. T is kept constant for Boyle, P is kept constant for Charles. What are we going to keep constant for Gay-Lussac? What will we keep constant for Gay-Lussac? Well, we've used up the T and the P. So for Gay-Lussac's law, we will take V constant and P, V will vary. Now I think it's kind of obvious what's going to happen. This time we'll take our piston and cylinder at pressure and volume. Sorry. We're varying temperature, my mistake. And we're going to lock it so that it doesn't get to move. We put the heat underneath here and we heat it up. Gay-Lussac, I think, was a balloonist, I'm not sure. And one of the reasons he was interested in this law was to see how balloons expanded under getting heated up. When you heat up a gas in a container, if you heat up a balloon, it gets bigger. But if you stop the balloon from expanding, the only choice instead of getting bigger is that the pressure gets bigger, right? So, Gay-Lussac's law basically says this: if you heat a gas up, the pressure gets bigger inside in the container. If we don't let it move, we put a lock here, and we don't allow any gas to escape from the container. We keep it all sealed in there. The same fixed mass of gas is always there. We're going to call this P over T C3. There's one other law which we refer to now indirectly only. If we double the mass of the gas at constant pressure and temperature, the volume is going to double too, or at least proportional to it. Now then, Avogadro's law will crop up later. We're going to combine our three laws. So we have Boyle, PV equals C1, no mention of temperature. Charles, V over T equals C2, a constant, no mention of pressure. Gay-Lussac, V over T is equals C3, constant, no mention of what? Of volume. So we take C1 times C2 times C3, we get another constant. Multiply a constant by a constant by a constant, you get a constant, right? C4 is an explosive. It's not constant. This is our constant. Let's put in for the three constants. C1, C2, and C3 is a constant, C4. P times P is P squared. V times V is V squared. T times T is T squared. Let's take the positive square root. We take a positive square root because we don't have negative volumes. So we get the expression that PV over T is equal to C5, in other words, always a constant. We get the first statement of the ideal gas law. PV over T is a constant. That means if we have a situation where we can measure pressure, volume, and temperature in the piston cylinder arrangement, the situation exists that P1 V1 over T1 for some configuration involving P1, V1 and T1 will always be a constant. It's always the same number once we keep the mass fixed. Now we'll do some examples in a minute, but this is basically what's happening. Let's have a closer look at this constant. The constant is going to consist of two parts because we'll invoke Avogadro's law. We'll call this constant C5 dash. Avogadro says that if we double the volume, we double this guy. In fact, depending on that constant, this can be n. And n is any positive number, okay? So, n can be any positive number. We've got a more general law, we'll write it like this. Our second statement of the ideal gas law . Well, we got that PV over T is a constant all the time. We're going to say this constant is going to be R for 1 unit of gas. Remember, we're keeping the gas fixed. PV over T equals NR, this new constant, and this new variable. So here's our statement of the ideal gas law. PV equals nRT, when P is in pascals, let's now go to P being in pascals, T being in Kelvin, and volume being in meter cubed. And what is N? If N is in moles, whatever they are, well, they are units of gas amount. They can be related to mass. If N is in moles, V is in meters cubed, T is in Kelvin, P is in Pascal, then R. R can be experimentally determined. Has to be experimentally determined, cannot be predicted. Well, actually it can in a different way. R is .314. 8.314 what? Let's solve for this one here. We need to be clear on the units for R. Right, I'm not doing this very well. We can show that the quantity PV is actually joules. So that the units of R are going to be joules per mole per Kelvin. So in the next little talk, we'll talk about the mole. What is it? It's a unit of amount. That's coming up.